it is very interesting phenomena. First of all, Zener diode works in reverse breakdown region called as Zener region. Okay, Zener region. You already studied about that breakdown and Zener breakdown when there is heavy electric field induced across the junction at the small voltage of reverse bias. In that case, you'll get some breakdown that is known as Zener breakdown. And another breakdown occurs that is just because of avalanche multiplication of charge carriers. Okay, that is called impact ionization. And this is the important line, that is Zener diode works in the reverse breakdown region called as Zener region. Okay, how it works. So this is the characteristics of Zener diode. You can see here. This is forward bias region, and here you can see this is the 0 volt line, and you see in the forward bias region, Zener diode is we are applying, this is positive terminal and this is negative terminal, you know well, and this is symbolic representation of Zener diode. Okay, this is symbolic representation of Zener diode. If you apply positive voltage on positive and negative voltage on negative, in that case this diode will be forward biased, and in that case this diode will be equivalent to a source of 0.7 volt if it is made up of silicon material. Okay, positive, negative. Fine, this will be equivalent to this in the forward bias region. Whenever we work in the reverse bias region, in that case, we can categorize this reverse bias region into two parts. This is first part up to here, and after this, this is second part. Fine, in the first part, this diode is totally off. Okay, and this acts as open circuit. Open circuit means we can call it like if Vz, this reverse voltage, applied reverse voltage, if here I am writing in forward biased region, it operates as battery of threshold voltage. Fine. And third line, this is very important. And hit it here, I'm writing. This is third line. In reverse bias, what is happening? In reverse bias region, first of all, first case when V is less than Vz, when applied voltage V is less than Vz. In that case, this acts as open circuit. Zener diode acts as open circuit. Fine. There is some flickering in my monitor screen. I think I would have to restart my system again. Okay, fine. Second case. So in the first region here, this diode simply works as open circuit terminal. Whenever this applied reverse voltage is less than Vz. Second case, whenever V is greater than Vz. In that case, this diode comes in the Zener region and it works as the voltage battery of this. Okay, this is plus minus, and this provide a voltage that is called Zener voltage, VZ. Fine, and Zener diode acts as a voltage source of voltage across it as VZ. Fine. So this is very important, and this is the only operation phenomena behind the Zener diode. I'm going to restart my system. You have to wait for 2 minutes approximately. That threshold voltage battery source. Okay. And here in the reverse bias region, we can further categorize the particular operation into two parts. In the reverse bias region, first region, it operates as directly open circuit whenever applied voltage, reverse voltage is less than, that is breakdown voltage, BZ. Okay. And here in the second case, whenever this VZ is breakdown voltage, whenever applied voltage, reverse applied reverse bias voltage is reverse biased voltage. Okay, if V is greater than VZ, in that case, this Zener diode simply acts as a voltage source of the voltage across it, that is across its terminal, that is equivalent to VZ. Okay, so and one more thing, this is the reverse biased voltage. This is positive and this is negative, and here we are applying positive and negative terminal voltage. So equivalently, this is working on positive and negative terminal voltage source. Fine. So this is very important phenomena. Now we'll talk about that some calculations related to this Zener diode. This is the simplest circuitry. And now I'll take for an example a circuit, simple circuit. Then we'll start working. There are three cases. Specifically, operation of Zener diode can be performed with three cases. First case, whenever V and Vi and R are fixed. What is the meaning of that? I'll tell you. Okay. Second case, Vi variable and R fixed. Third case, Vi fixed and R variable. There are three cases. First, we will study about the operation of Zener diode in the first case. And now Vi and R both are fixed. Okay. So first case, Vi and R both are fixed. Okay. So just taking an example. First case, okay. So here in the first case, if Vi, this is Vi and this is R. If these are fixed, specifically if we talk about both in this resistance. The second case here we will modify it little bit. This is RL specifically, this is RL specifically, and this is RL specifically. So here if VI and RL both are fixed, okay, in that case what will happen? It is a input resistance and this R is RL specifically. This is we are talking about load resistance. Okay, so in that case, this voltage, input voltage will supply a current here, and this will provide a current IZ. Okay, the current across the Zener diode, and then there will be some voltage drop plus minus. Fine. Now, this is very important thing. Whatever I am going to explain you, if you understand this phenomena, then it will be very easy for you to understand the whole concept. So first case, we have, I told you already, like there are two reasons in the general characteristics. First reason, if we apply reverse bias voltage is less than Vz. And second case, whenever V is greater than Vz. So here first case, we will check for first case and then second case. If V, whatever is the voltage across applied voltage, this Vi is, this V is greater than Vz, in that case what will happen, this diode will be acting as voltage source. Otherwise if V is less than Vz, in that case this diode will be acting as open circuit. Okay, we know the both cases. So first we will check. So first step we are going to check that the load resistance, the voltage across the load resistance, or simply first step. You keep this in your brain. Step 1. Step 1. Remove Zener diode and apply a voltage source of voltage V. Fine. So in the first case, I'm going to make some equivalent circuit. Here I have removed that Zener diode, and this is already Vi. This is R, and here this is plus minus V. I have applied here, and this is load resistance RL, and this is the voltage across this load resistance RL. This is PL. Fine. So in this case, first step we have applied a voltage source by removing this Zener diode. Okay, fine. Is there any doubt? No. So can we calculate the value of V? Yes, definitely we can calculate the value of V. So how we can calculate? Suppose this is current I. Okay, we first will calculate the value of this current I by applying KVL. So it will be minus Vi plus IR plus RL into I equals to 0. So I will be Pi upon R plus RL. This is equation number 1. Is there any doubt? I don't think there is any doubt. This is simple KVL I have applied. So now I will check the value of this V. The value of this V will be equivalent to VL, because these both are in parallel. So what will be the value of VL? And that is equals to IE into RL. Okay. So what is the value of I? We can take it from equation number 1. So it is R plus R. Okay, this is the value of voltage source whatever we have applied after removing the Zener diode. Okay, now check. If this V, first case, If V is greater than Vz, breakdown voltage. Okay, there is general breakdown voltage. In that case, diode will be, you know well, what is diode will be a source of Vz. Diode will be replaced by Vz. And second case, if V is less than Vz, then diode will be open circuit. Means this is first case or second case. Okay, simply this is simple conclusions. So this is the procedure how to, if you get any circuit like that, and so simply you will remove this general diode and you will apply a voltage source and you will calculate the value of this V across the general diode. If this V is less than the Zener breakdown, in that case Zener breakdown voltage, in that case in that case this diode will be open circuited, and if this is the first case, and in that case this Zener diode will simply be replaced by this VZ. Okay, I hope these two steps are clear to you. Okay, so in the first case we will assume that V is greater than VZ. Okay, if V is greater than VZ, in that case, so first case we are assuming that V is greater than VZ. Okay, so in that case simply diode will be replaced by VZ. So here I am going to replace this diode plus minus, this is Vi, and here diode from the voltage VZ. And okay, this is simply I have written VZ by removing the zero diode. Okay, now I can calculate the value of everything. Everything like if this is the Zener current across this branch, and this is total current capital I R, and here this is the load current IL. So I can write this, I can apply KCL at this node, and it will be IL equals to IL plus I Z equals to IR. Okay, and here in that case we can calculate the value Iz equals to IR minus IL. Fine. And in a simple manner, if we talk about this IL, then definitely this IL equals to the voltage across this resistance RL divided by this RL. Okay, and here if we apply KCL, are you familiar with this KCL? No? Is there a difficulty?
No, sir.
Yes, yes. So here, further note, if I just want to find this value of R and this IL, then here, what is the value of voltage? VZ. This VZ will be RL. In this manner, we can calculate the value of IZ. Okay, once we are able to calculate the value of Iz, we can calculate the power dissipated across this resistance, or power delivered, power provided, offered by this Zener diode. That is PZ equals to VZ into Iz. We know the value of VZ already, we calculated the value of VZ. Okay, and Iz we calculate right now, and then in that manner we can calculate the value of VZ. Okay, this is power dissipated by Zener diode. And in this condition, in this first case, Zener diode is considered as in on state. Okay, and here it is considered as off state. Second condition. I think this is very easy to understand. Yes, everything is in steps. Okay, here we have to solve one numerical so that everything should be very clear. example. Okay, we are going to solve a numerical problem, and it will be very easy to understand the concept, whatever we have studied right now. Okay, this is applied BI. Let me change my smart pad. Wait for one instance, and everything is given to you. This is 16 volt, and okay, fine. In the first case, question is for the Zener diode network. Determine determine BL, VR, IZ, and PZ. Okay, for RL equals to 1.2 kilo ohm. This is first case. Second case, you have to determine about repeat. Determine all values for RL equals to 3 kilo. Okay, so this is the question. Now we are going to solve this question in any way. Fine. So what was the first step? We have to check the voltage across, check the voltage across the diode. Okay, we have to check the voltage across this diode, whether it is greater than Vz or less than Vz. Okay, so we will calculate, we will replace this diode from a voltage source. First step we are going to follow that we have explained. Okay, here we are applying a voltage source of V volt, fine. And in the first case, first part I'm going to solve. In the first part, this is 1.2 kilo ohm, and here this is the value of R. This is 1 kilo ohm already given in the question, 1 kilo ohm, and this is 16 volt already given. Fine. So calculate the value of this voltage V, and this is simplest way to calculate this value. First determine the current across this branch, and then this V will be equivalent to VL. Fine. This is VL. Fine. So we'll calculate the value of this current. I equals to this is plus minus 16 plus I into 1 into 10 raised to the power 3 ohm, and plus 1 point I into 1.2 into 10 raised to the power 3 ohm equals to 0. So I equals to 16 upon 2.2 into 10 raised to the power 3 equals to 16 by 2.2 into 10 raised to the power minus 3. Okay, and we can call it like 16 upon 2 by 2.2 milliampere. Ampere. Fine. This is okay. Fine. This is the current. Now I'll calculate the value of V. So V equals to VL, and that is equals to I into RL. So this is equals to I is 16 on 2.2 into 10 raised to the power minus 3 into 1.2 into 10 raised to the power 3. This 3 cancel and point cancel. Now we can calculate the value of voltage. 16 into 12 upon 22. So this is 2, 6, 11. This is 96 on 11. So 11, 8, okay, 88, and it is 8. 8.73, yes. So here V equals to 8.73 volt. 8.73 volt. And already one thing is given in this question, that is Vz equals to 10 volt. Already this is given in this question, that Vz equals to 10 volt. So do you think now you got this value that V equals to 8.73 volt? And what was the second step? We have to check whether voltage across the diode is greater or less than Vz. This is already given in the question. Vz equals to 10 volts. So here we can go for V is less than Vz. So what will happen? Diode will be open, open circuit. That's very good. Okay, so here diode will be open circuit. So now if diode is open circuit, so simply we can calculate the value of different parameters. So in this case, we are going to make an equivalent circuit again, and by removing the diode by open circuit, okay, and this is now open circuited, okay, and this is load resistance, and here this is 16 voltage plus minus. This is resistance R equals to 1 kilo ohm, fine, and this is 1.2 kilo ohm. Now we have to find out the value of VL, VR, IZ, PZ. Okay, okay, what is the VL? VL we will calculate directly. What is the value of I we can calculate across this diode. Okay, so VL will be equals to I into RL. Can you calculate the value of I here? Can you can you calculate the value of I? Yes, sir. Yes, yes. You can calculate. Simply VR will be equals to I I into R. That's right. To the value of I. I'm not audible. Okay, let me join again.
So now what will be?
Okay, what will be the value of PZ? Power dissipated in zero diode?
Zero.
Zero,
Yes.
zero watt.
It will be 0 watt. Check for the second numerical. And we have to calculate the value of everything here. In the case whenever R equals to 3 kilo. Okay. So again I am making second part of this numerical. This is R equals to 1 kilo ohm, and here I have applied we have applied 1 zero diode, and it was offering resistance voltage VZ equals to 10 volt, and this one RL equals to now 3 kilo ohm, right? And here it was all the candidates are requested to keep themselves on mute. Okay, this is 16 volt. This is 1 kilo ohm, fine. So now again we will check whether this diode is this voltage across this diode is greater or less than VZ. So we will replace this general diode from a source or battery, and we will try to find out the value of that. And this is 16 volt, and here we have replaced this by B, and okay, and this is R equals to 3 kilo ohm. This is 1 kilo ohm. Okay, so now we'll check out the current I. This is open circuit actually. Okay, so if this is open circuit, so this is current I. This current I will be passing through these both resistances. So here I will calculate minus 16. I am applying this KVL minus 16 minus 16 plus I into 10 raised to the power 3 plus I into 3 into 10 raised to the power 3 equals to 0. Fine. So this I will be 16 upon 4 into 10 raised to the power 3. So this I will be 4 into 10 raised to the power minus 3 ampere. Okay. Now I'll calculate the okay. Now I'll calculate the value of this voltage V. So this V is simply this is VZ. Both branches are in parallel. V equals to VZ, that will be equals to I into RL, and that is equals to this is 12 volt. Okay, so here this is the important conclusion. We found that V is greater than VZ. So ultimately, this diode cannot be short circuited.
Okay.
Oh, open circuit. Open.
Simple.
Yes.
The answer.
To VL. So here we can say that if V is greater than V, now here we have calculated the value of V, and that is equivalent to load voltage, and this V is greater than VZ. VZ is already given. So if this V is greater than VZ, in that case we can say this diode will be acting as a source of 10 volt. Okay, so now if we got this conclusion now, then in that case we will replace this Zener diode from a source of 10 volt battery. That is 10 volt. Is there any problem? Equals to 3 kilo ohm and R equals to 1 kilo ohm, and this is 16 volt. Is there any problem?
No, sir.
No. This current you know well, in that case this is IL, this is IL, and this is IR. So here I was saying that IR equals to IL plus IZ, okay, and that IZ equals to IR minus IL. And here I can calculate the value of IZ. IR equals to, here at this node the value of voltage is 10 volt VZ. So it will be 16 minus 10 upon 10 raised to the power 3, 1 kilo ohm, minus IL. IL will be 10 upon 10 minus this 0, 10 upon 3 into 10 raised to the power 3. If anyone feels difficulty in this method of calculation of current, this is whatever I am applying, this is KCL. Please speak up right now. If you will not speak up right now, and if you will not understand this concept of KCL, applying KCL, then it will be very difficult for you to understand in the future the basic concepts. If anyone is facing
Sir,
a
for IZ, sir,
I
for
Z,
IZ, you will 10 minus 0, 10 minus 0 will be
we have to calculate IZ. We cannot do like that. We cannot do this like that because 10 minus this 0, we cannot do this like that. Because this is only voltage source applied in this branch. No resistance is there. Understood?
सर
Yes.
सर यहाँ केसीएल कैसे आप डायरेक्ट लगा रहे हैं इसको सब थोड़ा बताइए
Exactly. I just wanted to extract this question from your side. You are listening while sitting behind. Yes, this is very important point. So I am applying KCL simply. You just see, I am keep I am applying KCL in this branch at this
Yes.
node. Okay, I
Yes.
am applying KCL at this node. I am taking current one by one. IR, IL, IZ. Fine.
और नीचे सर आप जीरो ले रहे हैं 10 वोल्ट के निगेटिव साइन वाला
Yes, this is 0 volt. This is grounded now.
यस सर
Yes. So listen this. How we are able to apply this KCL directly. Suppose I have to find out the value of this IR. Okay.
यस सर
Okay. In that case, what we will do, we will take IR is the current in this branch. Okay. In
यस
this.
सर
So we will keep this current outside of this branch, whole branch outside. This is 16 volt. This is R equals to 1 kilo ohm, and this is VZ equals to 10 volt. Is there any problem?
नो सर
No. Means this is I can replace this plus minus 10 volt, and this will be the current IR. Okay. So I now apply KVL. So here minus 16 plus minus plus I into 10 is to the power 3 plus 10 equals to 0. What will be the value of I? That is I equals to 16 minus 10 upon 10 raised to the power 3. Whatever I have written here.
Yes, sir.
Understood?
Yes, sir. Got it. Thank you, sir.
Okay, and in the similar manner, you can pick this branch up. You can take this branch. I'm taking another branch outside. Okay, this is RL equals to 3 kilo ohm, and here this is VZ. VZ means plus minus 10 volt. And separately, if this is IL, separately I will apply KVL here. So this is minus 10 plus IL into RL equals to 0. So IL will be 10 upon RL. So whatever I have written here. Understood? This is very easy to understand. So again we can solve it here for IZ. Okay, so we can calculate the value of IZ. Once we are able to calculate the value of IZ, we can calculate the value of IL as well, and we can calculate the value of PZ. We have calculated the value of this VL we can calculate, VR we can calculate, IZ, PZ, everything we can calculate. Can you?